I make some or do I need to get some?
You need to get some.
Aye.
KSU.
All right. So here's, it's a little bit wonky how I got into the beginning of this, because normally, and I'm not gonna have a separate test over it, we're just gonna spend a couple of days talking about electrical potential energy, it's called EWE. And it gets weird because it's like other types of energies that you've studied, but it's weird because it can be negative, but we'll talk about that. So normally I cover that in the unit in the third 9 weeks. And that's usually included in that test. So I had to take that out of that electric fields test because we didn't get a chance to go over it because we lost so many snow days. So it's important that you understand it. I'm not gonna have a separate test over it. We're gonna have a couple of simple assignments on it just so you can get a feel for what those look like, because it's one of the most important types of energy that you can have, because without the ability to store electrical potential energy, like your cell phones wouldn't work. So imagine if your cell phones only worked if they were plugged into a wall, how your life would change. Because if you look at like when cell phones first came out, they didn't have very good batteries, and they were literally called bag phones because it was about the size of Deacon's lunch pail right there. That used to be the size of phones, and it was called bag phone. Because to have any kind of battery, it was massive because we didn't have very good battery technology at the time. So a lot of times you would have to plug your phone into, at that time, this is another thing that's changed with cars, almost every car had a cigarette lighter in it. And so how that would work is that a lot of people smoke, as opposed to vaping now. That's healthier. Okay? And so one kid made the comment like, what are they doing with bathrooms in the vape room? I was like, okay, that's a unique way to put that. So you would, how the cigarette lighter would work is that you would there was like a black knob about yay big, and you would push that in. And then the cigarette lighter was about the size of your thumb. It was a coil metal inside of that, and it would make contact, and then it would get red hot. And then you pull that out, and then you would touch that to the end of your cigarette. And that's how you would light your cigarette, because that's how people did that. And so you can't even get cigarette lighters in cars anymore, so that's how you kind of date the age of the car. Hey, did it still have cigarette lighters? So, but because that was a source of electricity, they developed the adapters to run the bag phones to plug into the cigarette lighter. So if you wanted to talk while you were driving, you would plug that into the cigarette lighter. Instead of lighting your cigarette, you could talk on the phone, and that was your source of energy, because the batteries didn't last very long. So we're going to spend a couple, so this is how the 9 weeks is going to play out. So spend a couple of days, literally today and tomorrow, talking about it. 2 days, boom, you're going to get it, not a big deal. Then from that, the first big unit will be circuits. Take us about 10, 11 days to get through that. Then the next big unit after that will be magnetism. Warning you now, that's notoriously probably the hardest test you're going to have. Okay, just because of so many conceptual things to it. And then the last test will be over like quantum mechanics and relativity and that.
And that test is easy.
Comparatively speaking, okay? There's no right-hand rule to E equals mc squared like there is to magnetic field. So that's how this is going to play out. So a couple of days on UE. Like I said, normally we cover this in the third 9 weeks, but we had so many snow days and everything else, I want to cover it, but I'm not going to have a separate test over it. Okay, so let's kind of go back, and it's going to be nice because we kind of revisit some old ideas. So if you look at the traditional way, and this is old school, of calculating UGG, what do you have? MGH, right? Okay, mass is in, G is in meters per second squared, height is in meters, you get kilograms meters squared over second squared. You can also write that as Newton meters. No matter what, you get units of joules, right? Okay, exact same thing. So if you look at kinetic energy, translational, 1/2 mv squared. That's also kilograms times meters squared over second squared, which also gets you joules. Now, there's another way to calculate gravitational potential energy. And if you look at gravitational force, that's big G m1, m2 over distance squared. Cool, all right? You've all seen this before, you've done computations with it. So you've got the gravitational constant of newtons meters squared over kilograms squared times kilograms squared over meters squared, and you're left with nothing but newtons, right? That's a force. Boom, we're off to the races, not a big deal. Another way that you can calculate gravitational potential energy is big G m1 m2 over d. So the only difference is that it's not d squared. You're just dividing by distance. But this is where this gets a little bit wonky in terms of conceptual ideas, and I need to begin to paint this picture. So I'm going to tell you right now, just straight up, conceptually, this is going to start off okay, but it's going to get weird. Okay, so just don't sit there and go, Bergkamp, everybody knows it gets weird, okay? Just don't act like you're the first person to make this observation. That's weird. We know it all is, okay? It's not a secret, okay? Just go with it. Now, here's how this is going to play out. So you still got big G, which is newtons meters squared over kilograms squared. And that's still kilograms squared. But now you're going to divide by just meters. Okay? Now you're just dividing by meters. So now what units do you get?
Newton meters.
You get Newton meters, which is the same thing as joules. So if you take those same numbers and you divide it by distance squared, you get newtons. If you take the same value of big G, two masses, and you just divide it by distance, you get joules. Okay? Now, this is where it gets wonky. And everybody fights this, but it's a conceptual view. So if you look at the traditional way to calculate UG, right? Traditional way to calculate UG. If I take this 1/2 kilogram mass and I lift it up, if I increase the height, what happens to the value of UG? It increases because it's MGH. Cool. If you calculate UG this way and you increase the distance, what happens to the value of UG? It becomes smaller. And everybody's at this point, why? Why? It makes no sense. Okay? So if you want a big UG using this one, what do you want the H to be?
Big number.
Big number. If you want a big UG this way, what do you want?
Small.
Small value. It's like, how can you be talking about the same conceptual thing? In one situation, you want a big value of height to create a lot of potential energy. In the next one, you want a small value of distance to create a big potential energy. Now, this is where you have to shift your focus. Okay? And this is going to play out also with electrical potential energy. So imagine that you have, here's the planet Earth, okay? And here is Will Stanley, okay, with his short hair.
To scale.
okay, to scale, right? And an even shorter amount of facial hair to scale, okay? Which looks really weird, by the way. Okay? Now, so in this situation, if you're talking about UG by calculating big G M1 M2 over D. So if you divide by a really, really, really big distance, okay, what's going to happen to that value of UG? Will is a long, 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 long way away from Mother Earth. We got a big, 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 big distance. What's going to happen to the value of UG? So in this situation, we have a really, really big D, so we're going to have a really small value of UG. Okay? Now, visualize this. This is kind of the ultimate mentality. The only thing that exists in the universe is the earth and will. That's it. Okay? Now, this is where work becomes part of the story. Okay? So, what did we have to do to get Will out to that point? We had to do work, right? Because Will was like, I kind of like Mother Earth. I kind of like Freddy's, you know? Like being able to get a haircut, watch the NCAA tournament. I kind of like Earth. If I'm way out there, this is kind of bad. Because Will is attracted to the Earth, right? So if we let go of Will is going to become closer and closer and closer, right? And in that regard, the kinetic energy is going to become bigger and bigger and bigger. Now, there's going to be a third piece to this puzzle. And this is also going to play out with electrical fields as well. Remember, at any point, your kinetic energy plus your potential energy has to add up to a constant. Okay, remember doing the simple conservation of energy problems where I lift this up, and if I store 2 joules of energy to lift it up, when it hits the ground, how much kinetic energy does it have? 2 joules. And the amount of work that I did in lifting it up was 2 joules. I store 2 joules of UG. I let go of it. It becomes 2 joules of kinetic energy. Okay, old school, right? Old school. It made sense. Now, here's where this is also true, but what's lacking on here, and now this will make sense, there's a negative sign lurking out here, okay? And you're going, whoa, how can you have negative energy? Because Burkamp, he always preached to us that energy was a scalar quantity and not a vector quantity. So when you look at this in terms of, this is where it gets weird, a little bit weird mathematically. So if you look at it in terms of Will being infinitely far away, okay? So if Will is infinitely far away, then as Will, and we did a certain amount of work to get Will out there. So because of the fact that that's a negative value, as Will gets closer and closer and closer, what happens to the magnitude of that UG as a negative value? It becomes larger, right? So as Will gets closer and closer and closer, so if you were to look at a graph of negative OOE versus distance. So if I've got a really, 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 really big distance, what's going to happen to the value of that negative value of OOE? Small. It's going to be really, really, really small, right? So as Will gets closer and closer and closer to the Earth, what's going to happen to the value of that negative OOE?
Bigger.
Gets bigger. So what's that? What do you think that graph's going to look like?
So you got longer than that.
Something like that. Okay? Because as he gets closer, you're dividing by a smaller and smaller and smaller value d. It's like, whoa, this is getting weird. I've got negative OOE. Weird. Okay? Well, wait, there's more. You know that the kinetic energy plus U has to add up to a constant. because energy has to be conserved, okay? So this number here, pick a number, make it 100, doesn't make any difference, it's just gonna be a number, so it's gonna be a constant. So this is some value, it's 100. So as you get closer, the OOE value, which is negative, is becoming a bigger and bigger negative number. So then to add up to the same value of 100, what has to happen to the value of the kinetic energy?
Just to get larger and larger.
It has to get larger and larger. So Will is going to be gaining negative OOE energy, okay, negative UG energy, technically, because it's gravitational energy. So he's going to be gaining negative UG to balance out an increase in the kinetic energy. So as Will gets closer and closer and closer, the value of his negative OOE is going to get bigger. So to produce the same mathematical value of 100, 1,000 doesn't make any difference, it's just a number. He has to be traveling faster and faster and faster, okay? So where work becomes a part of this, the work that we did to take Will from the earth, which he really likes, we had to do work to push him further and further and further and further away. So we had to do work to store negative energy, okay? So the reason that this works, and you're going to see why it works with OOE as well, and you're sitting there going, but this doesn't make any sense, why do you have negative OOE? The reason that this is going, if you understand this, and it makes no sense, you're sitting there, okay, it makes no sense to have negative OOE. But I need you to understand this concept so that when we apply it to electrical fields, we're going to have the exact same thing. Because if you look at how you calculate OOE, okay, electrical potential energy, or if you go back and look at how you calculate electrical force, that's KQ1, Q2 over distance squared. So if you remember about how you calculate electrical forces, okay, that equation, and that's newtons meters squared over coulomb squared over meters squared, and you're multiplying that by coulomb squared, everything cancels out and you get newtons, okay? Mathematically, OOE plays out the same way. It's going to be KQ1, Q2, but instead of dividing by distance squared, we're going to divide by just distance. And oddly enough, that's going to work out to be Newton meters, which is going to be joules. Now, this is where this is different. If you're talking gravitational potential energy, and there's that lurking negative sign out here, okay, right here, right there, which I know looks like lost in the jungle, but it's there. Can your masses ever be negative?
No.
No. There is no possibility with gravitational potential energy to generate anything other than something that is negative, because of the fact that masses are always going to be positive, so you have that negative sign lurking out there. But when you talk about OOE, because of the fact that you could have unlike charges, you could have two positive charges, you could have two negative charges, you could have a positive and a negative. So OOE also has a lurking negative sign out there. But because of the fact that it's possible, if you have like unlike charges, where that OOE could be positive or negative depending upon the situation. So UG can only be negative. OOE can be positive or negative depending upon the situation. Okay? But here's going to be the main idea. Work's going to be involved. You can still store energy, and you can convert that into kinetic energy. So, Danny, stop you on the camera. Let's go to the back of the room.